Hello, everyone. Please take your seats. So I'd like to welcome everyone to our October meeting of the Colorado Springs Astronomical Society. My name is Scott Donnell. I'm the current president. And with me in the room is Tom DeClue, our current treasurer, and who else? Oh, Brad Goodman, secretary, sitting right here, and trustee Matt Russell, and president-elect for this next year. And I should also mention that Tom DeClue is also our RMSS director. Who else do I have in the room in the way of officers? I know that Jim Erm is not here tonight, and I don't see Doug Cook.
Doug Cook is in Maryland.
Okay. So I'm not missing anyone else then. Okay. So then just a couple minutes up front, and then we're going to launch into our featured presentation. And we're going to, normally we do a kind of the business part of our meeting up front and then do a presentation in the second half. But our presenter is Dr. Stefanie Milam from Goddard Space Flight Center, and she's online with us. And it's 2 hours later there than it is here. So as a courtesy, we're going to go ahead and have her give her presentation as soon as I get the show of hands for new members and visitors. Okay. Dave, I know. So 2, 3. Let's start with you in back. Your name is, go ahead and stand up and tell us about yourself and your interest in astronomy.
Oh, okay. My name is Stefanie. I run a small observatory in Kansas City. I've been in astronomy since I've been 14 years old. Do mostly imaging there. So thought I'd come up and check you guys out.
Okay, now is your imaging, do you submit results to AVSO or CBA?
Mostly on Facebook, on the astrophotography website.
Okay, so you're an astrophotographer.
Yeah.
Okay, well then Brian Gibson is the guy you want to talk to right here. He heads up our astrophotography special interest group for the flight. So, okay, Dave, you're up.
Dave White in California. There are already several Daves here and several Whites, so it's easy. Dave from the outreach administrator,
Yes.
and then Steve White. Combine those two, and you get Dave White, which is me. I'm a super astronomer.
So, what part of California are you from?
Where is Northern California? I'm not in the fire. Chico San Francisco. Yeah.
All right.
Yeah. So I kind of got my first paid experience in astronomy out in the Atacama Desert, which is in northern Chile. There's this observatory there called the Atacama Large Millimeter Array and ALMA. And so I got the job where I was an English language star guide. And so the agency said, oh, we have tour now. We got people who want to see the stars. And so I would just take them out and point out the stars, and the space satellites. And so now my goal is to bring those skills here. I want to teach people how to use the astronomy app on their telephone. I mean, those things are not easy. Once you learn those things, like everything in technology, they're frustrating at first, but when you learn it, it's great, almost magical. When you get that eye, screen, star coordination going, that's what my goal. That's what I want to contribute.
Well, very good, thank you, Dave. And you, sir.
Yep. My name's Joe Santa. I'm a docent over here at the Space Foundation for the last 4 years. And we were here to do a certification on the Mars lab. And I thought I'd just sit in on your astronomy.
Well, thank you. Well, welcome. I should also mention we have another trustee, Floyd Blake, back there with the hat and his arm casually up on the chair next to him. So we have both our trustees here. Thank you, gentlemen. Dave Warner, our director of outreach, and a few others here too. So, in the interest of time, is there anyone else who is new member or visitor other than the? Oh yeah, sorry, I missed you. Sorry.
Dave Warren, I've been an amateur for 60 years and just thought I'd come see what's going on. I remember about 10 years ago, but things came up.
Yeah, you did. Well, welcome back.
I just want to point out the location of the paperwork.
Okay, well, Fred, stand up there and let people know.
For the visitors, We have the visitors cards on that table over there, so when you get a chance, please fill out the information. And for those who haven't seen it, that's where the attendance sheet is now located, is on the same table. So when you get a chance, please fill it out.
All right, thank you, Fred. And then Walter Warren has ID cards for new members. So if you are a relatively new member and look at your ID cards, see this gentleman right here. He's got a number of them laid on the table. So anything else to add to that, Walter?
If you haven't signed up, then I don't have one for
Okay,
you.
if you haven't signed up for a ID card, if you're a new member and you haven't signed up for Walter, then there will be one here on the table for you. So if you want one next time, see Walter and get signed up for that. All right, is there anyone else that I missed out there? Got everybody? There's a few slices of pizza, maybe about a dozen or so over there, courtesy of the Space Foundation. And I hope my cell phone doesn't go off in the middle of Christmas.
Can you say airplane mode? I knew you did.
Well, actually, just reminded me that I need to kind of shut mine down because I've got some weird ringtones. So what I would like to do at this point is to introduce our featured speaker for this evening. So we are pleased to have Dr. Stefanie Milam from the Goddard Space Flight Center to speak with us tonight on the James Webb Space Telescope. A little background on Dr. Milam. She works in the Astrochemistry Laboratory at the NASA Goddard Space Flight Center in Greenbelt, Maryland. She's an expert in rotational spectroscopy, and sometime I'm going to have to ask her exactly what that means. Observations and laboratory modeling of astrochemistry and molecular astrophysics of the interstellar medium, evolved stars, star formation regions, and comets. So a lot of the chemistry involved in those types of objects. Dr. Milam maintains a renowned observational program with radio telescopes around the world and with space-based observatories to routinely observe comets as part of an international collaboration. Additionally, she conducts high-resolution spectroscopic studies of evolved stars, star-forming regions, and the galactic interstellar medium, and she specializes in particular in the isotopes. Her key research objective is to study the isotope composition of evolved stars to determine the nucleosynthetic processes that have taken place, chemical enrichments that may occur in the mass balance process, a very interesting topic in itself, and how the enrichment is distributed to the interstellar medium, star-forming regions, and planetary systems. So think of an evolved star spewing stuff out into space, the details behind that. In March of 2012, Dr. Milam was selected as the James Webb Space Telescope Planetary Science Liaison. Under this role, she helped establish the next generation space telescope as a planetary science resource, engaged the community in future observations and preparations, and assisted the project to ensure the capabilities of the observatory were suitable for solar system observations. In July 2014, Dr. Milam was appointed as the James Webb Space Telescope Deputy Project Scientist for Planetary Science to continue her role through launch in 2018, well, now spring 2019, which is where the launch has been slipped to. Her presentation titled tonight is titled The James Webb Space Telescope. And before I say please welcome, please hold all of your questions until the end of her presentation. And then because of the status of the microphone, we have to kind of relay them to her close to the microphone. So allow her to do her presentation. Hold the questions till the end. So please welcome Dr. Stefanie Milam.
Thanks so much. Thanks for having me. I am happy to be participating in your meeting remotely, if anything, and a second try at giving this talk. A lot's happened, though, since the last time I tried to connect with you, so hopefully I can give you an update on what's going on with JWST, or the James Webb Space Telescope. The sound is better than what it was when we were testing it earlier, but maybe still hold the questions to the end just in case it is spotty and I don't quite hear your question. So as I was just introduced, I'm the Deputy Project Scientist for Planetary Science on JWST. feel free to follow me on Twitter or JWST on Twitter. My handle is down at the bottom if you're interested. So I'm just going to get right into it. The James Webb Space Telescope is not only a NASA mission, it is it's an international collaboration between NASA, the European Space Agency, and the Canadian Space Agency. The mission's being led out of NASA's Goddard Space Flight Center, where I work in Maryland. And our primary contractor is Northrop Grumman. We have 4 science instruments on this telescope that operate between 0.6 and up to 28.5 microns. Those instruments include a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, and a fine guiding sensor, which also has a science instrument, which is a near-infrared slitless spectrograph. The operations of JWST will be held at a Space Telescope Science Institute in Baltimore, Maryland. This is the same place that operates the Hubble Space Telescope. So they're very well studied in operating space observatories for NASA. There's a picture of JWST up here on the right, so you can see sort of what it looks like and what the scope of the observatory is, and I'll go over details of that in just a minute. It is an infrared telescope, so we do want the telescope to be cold, so we do that by actually passively cooling it in the large sun shield that we have. We will launch on an Ariane 5, which is being provided by ESA, or the European Space Agency, and we will operate out at the Sun-Earth second Lagrange point. We have 4 science themes, which I'll go into more details of. Our primary science theme and how the telescope was actually designed and our primary science goal was the end of the dark ages, so detecting the first light and reionization. But we also have other themes, since this is a full-purpose observatory, which include the assembly of galaxies, the birth of stars and protoplanetary systems, and other planetary systems, as well as our own solar system and searches for the origins of life. So who is James Webb is a question I get a lot, especially in the public or from students. James Webb was the 2nd administrator of NASA. He was the administrator during 1961 and 1968, or to 1968, excuse me. He oversaw the first manned spaceflight program, the Mercury program, as well as the Gemini program. But his main contribution, which is significant for those of us that aren't in the manned spaceflight program at NASA, is that he actually was a big advocate for actually doing exploration beyond manned spaceflight. So he oversaw the Mariner and Pioneer planetary exploration programs, in addition to further studies of our own moon with the Apollo program. So JWST is sort of an intermediate observatory between the Hubble Space Telescope and the Spitzer Space Telescope. These are 2 actually currently active missions. Everybody knows the Hubble Space Telescope. It's an optical to UV to the near-infrared telescope, primarily optical wavelengths. It's a 2.4 meter. It orbits around the Earth. And it has a very good field of view compared to a lot of ground-based facilities that we have, especially at the time that Hubble was actually launched. The Spitzer Space Telescope was actually an infrared telescope, mid to almost far infrared. It was cold the first part of its mission, so it was actually a cryogenically cooled mirror down to about 6 Kelvin. But the mirror itself was only 0.8 meters, therefore it had a fairly large field of view. So imaging wasn't quite as sharp as that of the Hubble Space Telescope, especially being at longer wavelengths. So JWST is going to be sort of the intermediate in between these 2 facilities, but also offering comparable angular resolution to what we had with the Hubble Space Telescope, just at longer wavelengths. So while JWST is called predecessor of Hubble, it's actually slightly different in that it operates from the near to the mid-infrared. So you can see on the bottom where we actually overlap between the Hubble Space Telescope and Spitzer, and then the horizontal scale is sort of our collecting area that we have. So JWST is 6.5 meters in diameter, which is quite large compared to Hubble and Spitzer. So JWST is going to be an all-purpose observatory or a general observatory. We have a 5-year requirement on the lifetime of the James Webb Space Telescope, but we have a 10-year goal. So what this means is everything on JWST has to be tested and proven to last for 5 years. But we also carry 10 years of fuel, 10 years worth of fuel. And we think that we'll be able to operate much longer than 5 years. Our engineers are really, really good, and they tend to over-engineer things. If we just look at, for example, the Chandra mission, which is an X-ray observatory, it was supposed to be a 5-year mission and is going on 18 now. Our primary mirror is very large, as I said, at 6.5 meters. So for those of you that can't do the conversion in your head quickly, that's almost 21 and a half feet. It's a segmented mirror because it's so large, and I'll go into details on that in just a second. Sorry, my dog seems to not want me to talk. We also have a sun shield, and I'll go over the details of this as well. It's quite large. It's about the size of a regulation tennis court. It measures about 21.2 meters by 14.2 meters, and in feet, that's also about 70 feet by 47 feet. We'll be at the second Lagrange point, as I said, and orbiting around the second Lagrange. That's about 1.5 million kilometers from Earth, or about 1 million miles away. We're passively cooled, so what that means is we cool the telescope just by remaining in the shade, and that gives us an operating temperature of about 50 Kelvin. I already mentioned that we had 4 science instruments. We're diffraction limited at 2 microns, so this is a near-infrared telescope. And the capabilities include things like filtered imaging, spectroscopy, coronography, and aperture mass interferometry. So here's our telescope. This is our 6.5 meter diameter primary mirror. So if you want to look at that with respect to scale of Hubble, we're a couple times larger than Hubble, quite larger than most humans. This is an average size, quote, average size man. I'm actually much shorter than average size, so JWST is like a handful more than just a few times taller than I am. The full observatory, when it stands from the spacecraft bus to the top of the mirrors, actually extends to over 2 stories high. Our sun shield, as I said, is about the size of a regulation tennis court, and if you want to know what that means in football terms, that means about 5 JWSTs will fit across your football field. Well, 4 if you want to take the halves off. So what this actually ends up resulting in is that we don't have a rocket that's big enough to fit a 6.5 meter or a 21.2 meter sun shield into any rocket fairing. So we actually have to fold the entire telescope up, and thus we give it the nickname of the origami telescope. So this image just shows you what it looks like when it's in the fairing of an Ariane 5. So you can see that it's completely folded up, and I have a deployment video that I'll show you at the end of my presentation. So how we actually cool the telescope and why we need such a large sun shield is because we have a very large mirror. The sun shield is 5 layers, and each layer is, it's made out of a material, it's sort of a highly engineered material, a Kapton type material with insulation on it. So Kapton is almost like a Mylar, which if you think of your happy birthday balloons that you buy, or Mother's Day, that's exactly what the material looks like and feels like. But each layer, depending on how close it is to the sun versus the cold side, has different levels of insulation added to it, basically just to help us cool the telescope. So the hot side operates at about 185 degrees Fahrenheit, and the cold side's almost minus 400 degrees Fahrenheit. So we have what they call an SPF of about 1 million on the cold side of the telescope. As I said, we're going to be operating at L2, but you can see that we aren't just stationary at this gravitational point. We're actually in orbit around it. This picture is a little misconceiving because the orbit in L2 is actually almost the same distance as the Earth to L2 distance. It's an extremely large ellipse, but it is quite far. We are never in the shadow of the Earth or the Moon. We always have direct access to the sun. So we do have a solar panel where we do operate with power, but we also have direct access to the Earth at all times, so we have communication. Because JWST looks so funny, and the telescope is actually in a fixed position with respect to the sun shield and the spacecraft, this means we have a sort of restricted field of regard. So we get an annulus around the sky at any given time, and we can't see due midnight with respect to the observatory. So our exclusion zone is less than 45 degrees anti-sunward and less than 85 degrees sunward. This allows us full access to the sky about twice a year. So we do actually see everything. You just may not get to see it at any given moment. So for solar system observations, this is something we're quite used to. It just means that we're not going to be looking at planets as they're closest to Earth necessarily. They're probably going to be made much closer to quadrature. So just a quick overview of what our operations are going to look like. There will be an annual call for proposals. None of the science time or partners have any allocated time. So in other words, we're not dedicating 25% to finding exoplanets or observing exoplanets and 25% to observing the first stars. NASA versus ESA versus the CSA doesn't have any time allocation either. It is absolutely 100% open time, and time will be allocated based on proposal pressure. And there is some guaranteed time that's been given to the instrument scientists and a few interdisciplinary scientists, but most of our time is actually going to go to guest observers. We offer non-sidereal tracking, which is important for observing things in our solar system. So we can track things with a speed limit of about 30 milliarc seconds per second or slower. And that's the fastest rate of motion for Mars. So that's quite significant for us. We have a data pipeline that's going to produce science quality data. So once the data is in the archive, you can go and pick out any of your favorite images of whatever targets you want, just as you've been able to do for the Hubble Space Telescope. We do support time-critical observations and targeted opportunities. We will offer funding to US investigators, so you get sort of a dollar amount per hour, and that dollar amount is impressive. It's comparable, well, it's not comparable to Hubble because Hubble is in per orbit. So it'll be a nice chunk of change if you actually get time on JWST. We cannot do Earth occultations. We can't look towards the inner solar system at the Earth or the Moon. So nothing of the terrestrial planets besides Mars. And near-Earth objects are a little bit more restricted. And I think I said everything else already. So this is our instrumentation in a single slide, what it looks like. So on the bottom you have wavelength, and then you can see the capabilities offered for imaging and spectroscopy with the different instruments labeled. So NIRCam is our near-infrared camera, NIR is our near-infrared slitless spectrograph, MIRI is the mid-infrared instrument, and NIRSpec is our near-infrared spectrograph. So you can see what wavelengths all the instruments actually cover. MIRI is the only thing that extends beyond 5 microns, but it does offer spectroscopy and imaging. JWST's performance is already outdoing everything that we know to date in the near and the mid-infrared. So this just shows you a plot of what our photometric performance actually looks like, so what our sensitivity is compared to Hubble. This is for imaging, I should say. Gemini Observatory, which is a large ground-based telescope, the SOFIA Airborne Telescope, the Spitzer Telescope, and then you can see in the light blue the JWST instruments, the near-infrared camera and the mid-infrared instrument. So you can see we're orders of magnitude better than most of these other facilities. So for spectroscopy, this is sort of the same plot. So this is showing you the sensitivity for medium to high resolution spectroscopy. Again, we have SOFIA, the VLT, which is another large ground-based telescope, as well as Gemini and Keck again, and then again Spitzer. So you can see spectroscopy, we really exceed performance on just about every single scale in the near and the mid-infrared. I have a few slides just showing you what our imaging and our spectral capabilities are. I apologize for the colors on this, and I don't know if you can see my cursor or not, but there are boxes showing you what our imaging capabilities are. So the field of view for the near infrared camera is about 2.2 arc minutes by 4.4 arc minutes. And then if you're actually imaging in coronography in the near infrared, it's about a 20 by 20 arc second. And in the mid infrared, it's a 1 by 2 arc minute field of view. And then there's other fields of view depending on if you're looking at different capabilities. And this is the same sort of slide for our spectroscopy. JWST has a unique capability for a space-based observatory. We are actually offering multi-object spectroscopy. So what this is a series of microshutters, 250,000 of them to be exact. These are tiny little hair-sized shutters that are opened by a magnetic strip, where you can actually look at a field of stars and open shutters to look at individual stars within that field and collect spectra on them. Stars or galaxies, whichever you would prefer. This is something that's never been done beyond Earth-based observatories. So this is a nice, unique capability for JWST. But also we have integral field unit spectrometers. So these are basically arrays where you get a three-dimensional image. So you get a spectra at every single pixel across this field of view. So you can see the IFU for the near infrared spectrometer is about a 3 by 3 arc second field of view. And every single pixel that we have across this will give you an individual spectra. And I'll go over some more details of that in a second. But we also offer slit spectroscopy as well as slitless spectroscopy. So we have full capability across all of our instrumentation. Our spectra is going to be so good in the mid-infrared and the near-infrared compared to previous facilities that we expect to learn quite a bit from it. This is just an example of a simulated spectra that we've done for a comet, because I'm a comet scientist. Showing you in the dark green line is a very rough, crude line that was actually a spectra that was acquired for Comet 9P Tempel 1. From the Deep Impact mission. So this was a mission that flew by a comet and dropped an impactor in front of the comet in its orbit and then collected spectra before and after. This was really exciting results, you know, a decade or so ago, because we were able to detect water, which is this large feature on the left-hand side of the spectrum, around 2.8 microns. Carbon monoxide and carbon dioxide, which is the feature on the right-hand side at about 4.3 microns. And then organics is what they called it, which is the feature sort of in the middle around 3.5 microns. You can see with JWST at our highest resolving power, we'll actually be able to resolve the water emission lines as well as all the individual organic components and distinguish between carbon dioxide and carbon monoxide, which is very important for us in cometary science. CO2 is a molecule that we absolutely cannot see from the ground. So I'm just going to briefly go over our 4 science themes and sort of what we're expecting with JWST. So just a reminder, our primary science goal that actually was the primary driver for most of the design of the telescope and instrumentation is to peer back in time, so into the first light, to see the first generation of stars and galaxies, how galaxies actually assembled and formed, how stars and planetary systems are formed, as well as studying exoplanets and planets within our own solar system. So the end of the Dark Ages is this realm in time after the Big Bang, where we've been able to measure the cosmic microwave background. So this is the excess energy left over from the Big Bang that's still remnant across the universe. Hubble Space Telescope was actually able to see, if you want to think of stars and galaxies as they formed in comparison to a human's lifetime, Hubble was able to see back to about toddlers, preteen ages of stars and galaxies and the formation of the universe. JWST is going to peer back to even further than Hubble was ever able to do. Because we're going to longer wavelengths, we're actually looking into the first stars and galaxies. So these are the infants or the toddler or the young babies, as it were. So this will be quite exciting. And the realm of possibility for discovery is just enormous for this field. Also being able to study how planetary systems evolve and form, so disk, both debris disk and as well as protoplanetary disk. This is something we're just now being able to access with the ALMA telescope, which I guess one of your new members was down there working with ALMA. ALMA is able to see longer wavelengths than JWST. It operates at radio to sub-millimeter wavelengths. So just the edge of basically what we can actually peer through in our own atmosphere. JWST really complements what ALMA does. They have about the same angular resolution, but they measure different things. So JWST is going to be able to determine the difference between the gas and ice content within a disk, whereas the ALMA telescope, the Atacama Large Millimeter Array, is actually looking at mostly the gas with a little bit of dust, but it only traces really small dust particles. So these two combined techniques actually really offer an enormous amount of insight into how these disks are evolving and how planets are being formed within them. Star formation is another huge area for JWST. So this is a Hubble telescope image of the Pillars of Creation in the Eagle Nebula. This is one of my absolute favorite pictures from the Hubble Space Telescope. But Hubble did have a near-infrared instrument on it for a number of years. And so it took the same image in the near-infrared, and what it was able to do was reveal stars that were actually being formed within this molecular cloud material. So I'll go back. Basically, all the light that is from stars either behind this formation or within it is being obscured by clouds, just the same way as clouds in our own atmosphere obscure the sunlight from us. The same thing happens throughout the universe whenever we have star-forming regions, which are these giant gas and dust clouds. It obscures any light either within it or behind it. So when we look at longer wavelengths, we're actually able to peer through that dust and gas, and we can see the new stars and how they're being formed, and even sometimes other objects of interest, including older stars and/or galaxies. Ice is a huge area of interest, especially for those of us that study chemistry in space. There was an observatory that was actually quite successful in measuring ices. This was the Odin telescope, but it obviously no longer exists, and it wasn't near as sensitive, basically because it wasn't as big as the James Webb Space Telescope. So you're really limited to what you could actually see through within those clouds, because in order to see through them and see absorption features of ices, you have to have a bright enough star behind the cloud to see the absorption. Since JWST is so much more sensitive than the other telescope, we'll be able to look at fainter stars, therefore we have many more lines of sight, and we'll really be able to probe what the ice chemistry actually looks like. Not only will we be able to see the absorption features of the ices, but we can actually even resolve where the ice and the gas lines are between these two, within a given target. So what this image on the right shows you is sort of a simulation. Actually, it's real data, but it shows you what a pure ice absorption feature looks like. And as you get to higher and higher spectral resolution, what it looks like when the gas features actually start coming out. So the bottom spectrum shows you what the ice and gas mixture would look like for a given target at a certain temperature at JWST's resolution. Exoplanets is definitely one of the sexiest topics right now in astrophysics. And JWST is really going to help revolutionize exoplanetary science. When the mission was first designed back in 1994, we knew of only one exoplanet at the time. We had no clue how ubiquitous they were across our own galaxy or even the universe. Since then, the telescope has actually, and the instrumentation has been modified and upgraded such that we are able to do exoplanet characterization and direct imaging. This is really, really important because with the spectral capability and the coverage that we have with JWST, we can actually look for things like biosignatures. So we have access to things like ozone, water, carbon dioxide, methane. These are all key ingredients that if they exist in a planetary atmosphere, that means they're probably supporting some sort of chemistry that's not abiotic. In other words, it's probably due to some other, possibly life-sustaining system. So how are we going to do this with JWST? Well, we have two main methods for detecting and characterizing exoplanet atmospheres. So the first is transit spectroscopy. So what we do is we actually observe as a planet transits in front of its star, and we measure the spectrum or the brightness towards that object as the planets go in front or behind them. And then what we can do is characterize these spectra. So whenever the planet crosses in front, the star gets a little bit dimmer, or the same as when it goes behind. And what we can do then is then translate that, that transit spectrum into what the actual species are within a given atmosphere. There's been a number of studies and papers written about what JWST is going to do for exoplanet science, and I'm certainly not an expert, so I encourage you to go to any of these references. And there's many, many more that come out almost monthly, so please look to those references if you're interested. This is the same method for how they actually discovered the planets of the TRAPPIST system with the Spitzer Space Telescope. So what they did was they stared at this star and they watched the actual flux from the star drop in various intervals. And once you look at all these intervals and you go through and you try to pick out the patterns, you can see that they found a pattern and they labeled it with these different colors. Each of these different colors represents a different planet. Therefore, they were able to actually then pull out what the transmission spectrum looked like for each planet and have been able to determine how far away they were from its star. Spitzer, unfortunately, doesn't have a spectrometer anymore of any sort of resolution. So knowing what the planetary atmospheres of these bodies looks like is still to be determined. They're working on it from the ground, but JWST will certainly exceed the performance of any facility that we have on the ground to date. So this is something we're really looking forward to, just to know what these planets actually look like, what their atmospheres are made of, if they're terrestrial planets with atmospheres, for example. The other way we look at exoplanets is through direct imaging. So this is basically where we take an occulter and we put it in front of the starlight, which dims out the starlight enough that we can actually see anything else around it. This is coronography. This is a technique that's been used on the ground for quite a while now, and is something that we really think will, JWST will be optimal for, especially at wavelengths that we don't have access to from the ground. We can also look at everything in our own solar system, well, almost everything. As I said, we'll be at the second Lagrange point, and we can't point anywhere closer to the Earth. We can't look at the Earth and the Moon, but we can do everything from Mars on out. So this includes all of our asteroids, all of our giant planets and their satellites, and the outer solar system. We can look at near-Earth objects and comets that come into the inner solar system as well. JWST is an extremely sensitive telescope. It's really big, therefore, and it's been designed to detect the first stars and galaxies in the universe. So it was a worry that it was going to be so sensitive that we couldn't actually look at things in our own solar system. Mars, for example, is the brightest object in the mid-near infrared sky. But we were able to come up with capabilities in our instrumentation by using subarrays, where we can actually employ them to look at our giant planets as well as Mars even. This is just an example of saturation limits on one of our instruments, the near infrared camera. And what you see is the Jupiter spectrum in red, Saturn in blue, Uranus in yellow, and Neptune in purple. and Mars is this dashed line on the top. So for this particular subarray, which is not our smallest one, you actually have full access to the Uranus and Neptune system, and you can image the full disk at a time. In certain bands, you can actually image the full disk of Jupiter and Saturn. Mars is challenging. You have to go to narrow filters and you have to use very specific windows, but you can still do full imaging. As I said, we do have smaller arrays, but you won't get the full disk. You'll have to do sort of mapping type observations. But Mars is extremely important to us. There's a lot going on with Mars and a lot of discoveries that are being made and need to be continuously observed. For example, water has been measured on Mars a number of times now, but this is really challenging to do from the ground. Water is in our atmosphere, and it causes a bit of a challenge when you're trying to analyze the data and produce full maps of Mars. Additionally, we have restrictions to how often we can observe Mars. We can only observe at night. The sky has to be clear. And we're generally only seeing one hemisphere. Whereas JWST can observe 24 hours a day, so we can see Mars at any given time that it's in our field of regard. And we can get the full disk and actually image Mars, and not only water, but as other organics as well. So this is going to be really important and a nice complementary technique that we can actually offer to the orbiters, the landers, rovers that we have for Mars, as well as ground-based facilities. Because we get full disk imaging, we can actually study real climate effects, see how the night to day variations in different species, including oxygen, water, carbon monoxide, methane, actually change. Whereas an orbiter, for example, only gets a direct swath of a very limited area of the planet. So to get a full map, you have to keep coming back to it. The same you have to do from the ground. So JWST offers that complement. As I said, we can do the giant planets. I already showed you what we can do for imaging and various components in their spectra. We do have missions that have been at Jupiter and Saturn. We've imaged it. Hubble does great imaging for us. But JWST operates at wavelengths that none of those facilities have ever offered, at much higher angular resolution and sensitivity, so it won't take near as long to do. So we can definitely study and actually continue the studies of these planets. Since they do vary with season, we do see things like storms come up, impact events, etc. So this is something that we should have access to with any observatory. And I'm happy to say that JWST will be supporting these observations. One of the big hot topics in planetary science right now are ocean worlds. So we know a number of our satellites have what we consider to be subsurface oceans, or evidence that they once had oceans. So this is the Hubble Space Telescope image of Europa when they discovered the plumes of what they think to be water. What I show on top of it is what our near-infrared spectrometers, integral field spectrometer pixel scale looks like on top of Europa. Basically, what you're seeing is these 0.1 by 0.1 arc-second spaxels, so spectral pixels. So each one of those squares actually offers a full spectrum that you see popping up there on the right. So we'll actually be able to study not only the plumes, but if there's deposits of the plumes actually on the surface and how they may or may not vary. We also have access to Titan. Again, here this image on the right shows you what that pixel scale looks like across Titan. It's nowhere near as good as Cassini, but again, we operate at wavelengths and spectral resolution that Cassini didn't offer. So we'll really get a good characterization, as well as long-term studies of what Titan, as well as Saturn and the other satellites actually have, how they've evolved since the end of the Cassini mission last month. We can do this for all other satellites as well. This is one of my favorite figures that came out of a series of papers showing you what the Cassini spectrum looks like in the mid-infrared. So this is the same wavelength to the right of the red line that JWST covers. So this is the Cassini SEER spectrum. And basically you can see all kinds of organics as well as carbon dioxide, hydrogen cyanide, ethane, hydrogen, etc. These are kinds of things that actually vary seasonally on Titan, and we can actually observe them and do better and extend the wavelength range than what Cassini actually had to complement what that mission accomplished. The small bodies in the solar system, actually in the outer solar system, are our bread and butter with JWST. These objects are small, fairly dark, and very hard to see with ground-based facilities. The sensitivity of JWST, as well as the wavelength coverage that we have, is very keen to observe, detect, and characterize these small bodies, including the major ones that we all know and love, such as Pluto. More recently, the detections of rings around other small satellites. Haumea, I believe, is the newest one, and they're satellites, but we can also do even smaller bodies down to tens of kilometers in size, including the next New Horizon target. So just a comparison for what we're used to. So this is what the Hubble Space Telescope was able to see with Pluto. This is the best that we had for Pluto before the New Horizons mission actually encountered it, but you can still see the variations across the surface. We do see a large white spot in the center image, which is the exact same white spot, or the heart of Pluto, that the New Horizons mission was able to measure. So when we compare that to what New Horizons saw, this is our ground truth now. So we have the large white area. This is basically a giant nitrogen ocean, frozen ocean. This red area is comprised of organics. We know this based on the very limited spectral coverage that we had with the New Horizons mission. It did have a spectrometer that operated it in the near infrared. So when we looked at the pixel coverage, or the spatial coverage that we had from the New Horizons mission, we could see the variations across the surface, as you see in the spectrum shown on the right. JWST is going to do more like this. This is a ground-based spectrum that was actually taken from Keck, I believe. No, sorry, from the VLT in 2008. But you can see this is the full near-infrared spectrum, and you can see how it actually varies. Pluto is going to be in a very different position with respect to its season compared to these observations, which are quite challenging to do. And we'll be able to do in less than 1,000 seconds much better than this spectrum that's shown at much higher spectral resolution. Not only can we do this for Pluto, as is shown here, but for all the other satellites, as well as other minor planets in the outer solar system. I'm going to start moving a little quicker, just so I can get through this. Small bodies, again, asteroids. These are another big hot topic, especially for planetary protection. So being able to characterize these small bodies is really significant. Additionally, looking to see if there's volatiles that are deposited on the surface. So if they did have an ocean or any sort of water or hydrated minerals in their composition, this is something that we can't do from the ground. So having access to the wavelengths that JWST has will really help us characterize these bodies. Oops. Oh, well, that's not supposed to happen. One second, I'm going to delete that. I don't know why that did that. So just a brief status of where we are with JWST. Currently, we just finished the testing of the optical telescope. So this is the mirror with the instrument suite attached to the back of it. What we did was a full end-to-end optical test down at Johnson Space Center in Houston, Texas, in Chamber A. This is the only cryovac chamber large enough in the world to hold the James Webb Space Telescope and its instruments. The reason we did this was basically because we're not going to be servicing JWST. It's 1 million miles away from Earth. And we don't want to run into the same complications as the Hubble Space Telescope had with focusing. So what we did was we put the telescope in space-like environment, so under vacuum and extremely cold, and we practiced focusing our mirrors, each of those 18 segments. to make sure that we could make them move the way we wanted, such that we had a telescope that looked like one single mirror. There was a hurricane that happened during this testing. Harvey actually hit Houston. Fortunately, we had a wonderful team that actually worked through the hurricane, even though we were at reduced testing levels instead of a full 24-hour day. Most of them were working at limited or more restricted hours, mostly because their own houses were flooding or their peers or colleagues were. But we were able to maintain testing through the hurricane and successfully complete all of our testing. As I said, we just completed. We just actually warmed it up. It takes a month to cool down and a month to warm up, so we just reached our warm temperature. We do have our space sun shield. Oh, and this is a picture of what JWST looks inside that chamber. So this is chamber A. This is where the Apollo capsule was actually tested. So astronauts went in there under vacuum and practiced getting in and out of the Apollo capsule. The JWST project actually went into chamber A, cleaned out all the fake lunar dust and old grease and oil, and made it a clean facility that operated under cryogenic temperatures. So you can see the tiny little people there at the bottom. This is an extremely massive facility. We do have our flight sun shield done. This is a picture of what it is, or what it looks like, or what it looked like about a month and a half ago. So all 5 layers are completed. This is them practicing folding them such that they will be for the deployment sequence. So our sun shield is now complete and being installed onto the spacecraft. A lot of documentation has been updated on JWST. If you're interested in reading anything about the telescope, the instruments, the science, the proposal calls, anything going on for JWST, you can find it here at jwst-docs.stsci.edu. Also, we had our very first proposal call come and go. This was for the early release science program. What the early release, I'll go over the details of that in just a second. Yeah, I think I have another slide or two in just a moment. You may or may not know that we have announced a launch delay. We've been delayed about 6 months. This is due to the significant amount of activity that still needs to happen. Basically, what we want to do is mitigate all the risk that we can. We do have a fully deployable telescope, and there's a lot of things that have to work. And we want to make sure they work very well. It was not anticipated how complex it would be to try to simulate a non-gravitational environment with such a large observatory. So the project came to the realization that actually testing all of our deployments was going to take quite a bit more time, so we do it right and carefully, that we don't compromise any of our hardware. So what's going on and what's happening? So as I said, we just finished our cryovac test of the telescope and the instruments. That whole telescope assembly then goes down to Northrop Grumman in California, where they'll practice a few deployments post shipment, so we can make sure that once it flew to California from Houston, everything's still working properly. Meanwhile, in California, as I said, we've finished the sun shield and we put it onto the spacecraft. We have a few deployments of the sun shield just to make sure we fold it and store it, as well as deploy it properly and know that everything works the way it's supposed to. There's some environmental testing that needs to happen on that, and some post-environmental testing that has to happen to that before we actually put the telescope onto the spacecraft and the sun shield. And then we have a number of other tests that actually have to happen. So you can see we have a really tight schedule, and as I said, it's just a very complicated observatory. Oh, again, my stupid thing didn't work. I don't think that matters. Okay, so as I said, we had our first proposal call come and go. This is the director's discretionary time for the early release science. Basically, what happened was the Space Telescope Science Institute was advised to offer some science to the general public or to the community that would be accessible before they write cycle 2 observing proposals. This all came about because of proprietary period of any data that's acquired in cycle 1. So all the programs that are going to happen the first year of operations for JWST have a 12-month proprietary period. In other words, anybody that collects that data, that's the primary investigator, actually has the only access to that data for a full 12 months. Proposal call will actually come and go before most of that data is actually available to the community. So it was advised that there should be some data for the community to have access to so that they can write better proposals for the second year of operations. So the director has allocated 500 hours of time. This was an open call. 106 proposals were submitted from 38 countries. Over 3,700 hours were proposed for, and only 500 are going to be awarded. The committee's actually met and has ranked their proposals. They're all going, the top proposals are going through a technical review right now, and the announcement of those that are selected will be very soon, hopefully within the next few weeks. This is what the science program that was proposed looks like for the 3,700 hours. So there were 5 solar system proposals submitted, 33 galaxies and intergalactic medium, 9 on cosmology, 19 on massive black holes, 10 on planets. This is exoplanets. I don't know why they just say planets. Astrophysicists, I guess, don't realize we have planets in our solar system. But planets and planet formation, there were 10 proposals, stellar population 13, and stellar physics 17. So it's a nice interdisciplinary program that was actually proposed for. So this looks really good for future submissions with JWST. That being said, we have our first official General Observer call for proposals coming out the end of next month, about a month away. And this will be open to basically anybody in the world. Oops. I just did. However, the one restriction that we have on the GEO proposal call is that none of the observations for the guaranteed time, or those that are selected for the early release science, can be proposed for. So you have to know what that science program actually looks like, which will be released in early December, so just after the proposal call. The actual deadline is in March of next year. It's right around the corner. And as I already told you, our launch has been postponed now to the March or June of 2019. We have 6 months worth of commissioning that has to happen before we begin our full science operations, which thus puts us down to operations around September to December of 2019. This is what that timeline looks like, showing you where we are and where we're going. So as I said, the early release science time allocation committee has actually already met and has made their prioritization of proposals. These will be announced shortly before the General Observer Cycle 1 call for proposals comes out in late November. And again, we launch mid-2019. If you want to know more, Google JWST is usually the easiest way to find it. But I will say, if you're interested in the status of testing going on for the telescope or what our major milestones are, those are all listed and are available to the public under this link at the top of the page, so recent accomplishments, which you can find all of this through the NASA JWST page. We have a webcam if you want to see what's going on in our testing facilities and actually see the telescope. I already mentioned the documentation pages, and most of the other documentation or information that you need will be either at the Space Telescope Science Institute or the NASA JWST page. And if you're supportive of astrophysics missions, I highly encourage you to let your congressman know and tell them that you're really excited about JWST and other future astrophysics missions. So with that, I'm going to thank you. If you have any questions that you can't get answered today, please feel free to contact me. My email address is here, and the organizers also have it and can forward any questions that you have. I'm going to play our deployment video and open up for questions, though, as that plays. So thank you for your time.
swap the microphones so we can put questions and change your cameras. All right. Voice in for the time being. Who has the first question? Hold on 1 second.
Okay, can you hear me okay?
I can.
Can she switch her camera so that we can see her?
Do you want to watch the deployment video or you want to see me?
No, we want to see you.
Okay.
And your dog too.
Yeah, sorry. He gets very jealous when I don't pay attention to him. Oops.
There she is. All right. Hello. So we have a question from Mr. Fred Goodman. Fred, go ahead and state your question, and then Stephanie will have Stephen relay it through his microphone.
I can actually hear you fine right now.
Okay. So Fred, if you would, and anyone else asking a question, please just raise your voice. Go ahead.
First of all, thank you very much for the presentation. Very enjoyable, and a lot of people will be diving in and trying to see what they can get developed from the data that they've captured over the years. My question has more to do with the imaging. With the delays that have occurred and the one that's coming up now, will that afford more time to investigate newer generations of sensors to hopefully even improve further the capability?
No, all of our instruments have been fully tested in environmental conditions. So we had 3 actual environmental tests that all the instruments went through. So that instrumentation is now frozen. There's no way to really upgrade it within the limited amount of time that we have, even with the delay. So if we had to employ, for example, new technology that's coming out or has recently come out, that technology isn't advanced enough to actually fly in a space mission. It has to have a certain technology readiness level before it can actually be put into space. So new technology, in order to advance to that phase, it takes quite a bit of time and actually money to get to a flight readiness level. So no, our instrumentation is actually, we have the newest detectors were installed 2 years ago. So we have the newest that can be flown on a space telescope.
So I'm going to go ahead and turn up the lights so we can see her, but she can't see us. So here we go. Ready to wind it here. All right. Okay. Next question. Who has the next question for Dr. Milam? Jason.
All right, it's almost a little bit morbid, so I wondered whether I should even ask this, but I'm just going to go and do it.
Make sure you project so she can hear you.
I'm used to it.
In the event of something catastrophic happening, I'm just curious, is there any backup James Webb telescope? I don't know if it was true from the movie. Just curious, so I'm asking.
No, there is no backup telescope. I don't think Congress would have given us enough money to build a backup telescope. All right. So the way we're dealing with this, how we've reduced the risk, is we've had an absolutely extensive testing program. So what we've done is we are doing all the environmental tests that we can possibly do on all the subsystem components. So just the instrument suite, just the telescope, just the sun shield, just the spacecraft, putting it through the whole rigmarole of, flight environment, launch environment, etc. Then as we assemble each of those components, we're also putting it through the testing. This was the original reason why the timeline of JWST got pushed back originally. All this testing actually is quite time consuming, costly, and it takes a lot of manpower to, put the telescope into a giant cryovac chamber, fully deploy it, fully stow it, analyze all the data, make sure everything worked. Did anything break? If it broke, we have to go back and we have to fix it. We have to figure out why it broke. So our test program is our primary mitigation for anything catastrophic happening. Additionally, we have redundancy on almost all of our mechanisms. So since it does deploy, it does unfold, there's redundancy on almost every single mechanism, especially our primary mechanisms. So when we, for example, unfold the booms for the sun shield, there's redundancy on those. We also have full control up in Baltimore on each of those mechanisms, and we have real-time sensors to know whether or not the deployment was fully successful or not. So that, in a nutshell, is what our risk mitigation is for anything catastrophic happening. I will say if anything happens during the test program on the ground, we do have backup mirrors. We do have backup mirrors. There are some backup detectors. There are some backups for some of our instrumentation. There is no backup sun shield. We do have a test sun shield, which may be thrown in as the flight one. But otherwise, JWST is the telescope as it is. There's no background or backup structure or full instrument suite or observatory.
So although I would like to add, Stefanie, that there is the time-honored cross your finger method, right? Especially during launch. So, Jason.
Thank you very much for the very complete and wonderful answer.
Brian, you had your hand up, and then Floyd, I'll come back to you. So, Brian.
All right. I have two questions. But we've been waiting for this for a long, long time. I can't remember how many years it's been, but it's very exciting. Two questions. One, maybe it's not a very fair question, but what are the two most likely things that could go wrong if something were to go wrong and be not necessarily catastrophic, but something would fail?
Now, just to be clear, our group, we're not focused on failure.
It's okay. I'm used to it. I will say this much, though. We were able to land a Volkswagen on Mars with nothing but a parachute, and it's still operating. So NASA does pretty incredible things.
The second question is, what kind of pixel resolution is the most sensitive device that you have for the infrared, sensing camera?
So the resolution of our pixels. So our pixel scale, it was on one of my charts. Let me look it up so I don't give you the wrong number. Because I would.
Well, I think a related question might be what size pixels? Are these like 9 micron or 24 micron pixels?
No, they're not that small. I don't know what their physical scale. I know what their angular scale is. I don't know what the physical scale of each of those are. I can say on the microshutter array, those are, each microshutter is about the width of a human hair and the length about 2 human hairs. If that gives you a sense of scale for the microshutter array.
Thank you.
Floyd, make sure you project, please.
I saw on your chart that fraction limit was 2 microns or 2. You're going to operate down to 0.6. How do you
We definitely lose sensitivity as we go down. I don't know if you remember on the sensitivity plots that I was showing, but when we went down to the lower end of the near infrared towards the optical, it swooped right up and basically met the Hubble value for sensitivity down at 0.6 microns. So we do lose quite a bit of sensitivity as well as resolution element. But we do have observing capability or techniques where we can try to oversample down at the lower wavelengths, which gives us some of that back, but not all of it. Our best resolution is definitely in the near infrared.
When you're imaging exoplanets, do you have the capability to be able to distinguish if you got an atmosphere, things like oxygen, methane, any of the biomarkers?
Yes. So with the coronagraph, do we have that capability? We do have filters in the coronagraph, and I think they have been defined at key biosignatures. If I remember off the top, I'm not as familiar with the coronagraph, I apologize. But those filters have been defined at key biosignatures, so like water, CO2, methane, and I think oxygen is one of the other. Oxygen's, I think, in one of those bands. And it's low spectral resolution too for the coronagraph. Now, transit spectroscopy, we get the full spectrum, so obviously we'd have more access to looking at what and characterize what an atmosphere looks like.
Okay. Any other questions? Going. All right. Well, once again, thank you, Dr. Milam, for your presentation, for our questions and answers. So again, please join me in thanking Dr. Stefanie.
Thanks so much for having me. Do you want me to play the deployment video, or do you just want to look it up online and watch it later?
If I can see it, please play it.
All right, let me present.
And I'll turn off the lights for that one.
And I can kind of talk you through it a little bit if you're interested. I'll at least point out the key things. So this shows you what JWST actually looks like right after we depart from the rocket and we release the fairing. So you can see it's all folded up in its little origami state. On the bottom of the screen, you'll see our distance from Earth and the Moon. And as each event actually happens, that distance is actually quoted, as it is here. And then the emission elapsed time is at the top, so you can see how many days it takes to do the full deployment and how long it takes. There's only 2 deployments that are not controlled from the ground that are automatic. The first is the the solar panel, because we need power. And the second is our communication satellite, so we can actually tell the telescope to do the other deployments. We do have a battery on board, which is good for a couple of days. But as soon as we get solar power, we cycle off of battery power. We do have communications. We have access to the ground about every 12 hours. I think we're scheduled every 24 hours, though, to do down and uplink. These 2 booms hold the sun shield, and basically the sun shield is folded up within them, but there's also a protective covering that's around them. This is to keep things like dirt, ice, or any debris from the launch actually condensing onto the surface of the sun shield, which is really important because any bit of that would actually cause scattered light effects for us. Some statistics on JWST's data. We have hold up to 471 gigabits, bits, not bytes, on board. There's about 329 gigabits for every 12 hours of science data that's collected. JWST operates on 2,000 watts of solar energy. Our solar array, gives us 2,000 watts. And our downlink rate is 28 megabits per second. Oh, I do have the numbers on the pixels. So the near-infrared spectrometer has about 4 million pixels across it, each of the detectors. The mid-infrared instrument has 1 million pixels per detector. One of the fun facts about the sun shield as it's deployed is we can't just basically pull it out and tension it. So basically just release it. We actually have to release or pull it out sort of in segmented. I think they're segmented about 2 feet segments. This is because it's such a lightweight material that if you just release the whole thing, it'll flop around until it's tensioned because there's no gravity. So all that flopping around could actually pose a risk of tearing it. So what they did was they created these cool little contraptions, which are basically magnets on a piece of elastic. So once the tensioning starts happening, it pulls the sun shield until the magnet basically detaches, and then it releases the next segment and the next segment. So it's really quite cool, the technology and innovation that went into doing a deployment of something like this. You can see we're now at day 12, and it's starting to look like a telescope. We don't have 7 minutes of terror. We have about a month. Everything's done in a very sequenced event. As I said, contamination, so any ice condensing onto the mirror or onto the sun shield is really important to avoid, or even the instruments. So everything gets turned on at a certain point or is deployed at a certain point in a certain temperature of the telescope, just to keep that contamination down. So it takes about a month to get there and to fully deploy the telescope and turn all the instruments on. And then it's another 4 to 5 months of actually testing the instruments, making sure we know how to point the telescope, and beginning before we can actually begin operations. So it is quite complex. All right, that's all I have.
Okay, thank you very much. So we want you to present every month now. But thank you very much, and I know it's 2 hours later there, and so feel free to log off. We're actually going to go into a break and then conduct our club business. So again, thank you very much.
Thanks for having me.
Thank you. All right, so we're going to go into a break here. A couple of things administratively. Again, Walter has got the name tags if you are expecting to have one. If you need one, sign up with him. Also, in the back are the new member, or the visitor cards, aka Fred Goodman's thing, and there's also the attendance roster. So if you haven't signed the attendance roster, it's on the back table. And then just before we go to we're going to have to kind of a short break here. Tom McClue wants to talk a little bit about RMSS artwork.
Yeah, real quickly, in case you hadn't noticed, we've got samples of artwork on the table here. We will, after the break, have a little contest to decide, and a selection process, decide which one we're going to go with. So during the break, you come out, take a look. I would say choose your first and your second preferred pieces of artwork. From here, we've got a total of to choose from, 8 or 9. So take a look at those, and then after the break, we'll hold a little contest to see which one gets chosen. Okay?
Okay, so let's take a break and let's plan on reconvening in 12 minutes. Sorry, it can't be longer, but at top of the hour, 8 o'clock, let's reconvene back here. We'll conduct part 2 of the selection. We'll complete our club business and call them back. Our kind of ongoing arrangement with Space Foundation hosts here, which we thank them for. To kind of run things along a little bit. Tom, please talk about the artwork for RMSS.
Okay, so hopefully everyone's had a chance to take a look. In the numbers, right? Number 1, three A and B, right? 4, 5, 6, 7, and 8. And as you recall, you know, the theme, obviously the theme is at opposition, the width of RMSS next year, so that would be the opposition or something like that. Okay, so that's why pattern is the way I'd like to see a show of hands. When I say number 1, show of hands, I'm showing twice. And I'm simply going to rely on the honor system here more than 2 times.
So quick question before, summer, like really full color, is that
Right.
a worry when it comes to merchant?
I think it is, and the reason I say that is because I go more than a quote for color unquote or design. However, using 4 colors to blend those to get color design. So these colors, all of these are acceptable at this point. Let's get started. Number one.
You could go 2. All right.
Okay. Got it, 12.
2. Three A. Three brother. Quattro. Okay. 5. 5.
No takers.
Okay. Wait a minute. I went from 3A to 5. I went to pick up.
No, you did 4. You did 4. You did 4.
Remember, vote off. 7. And finally, number 8.
We did a, you know,
Just do that again. So that
well,
was 3 and 4.
that's 3 and 4. so we missed the line. It had to be one of these black and whites, like 6 and 7, almost. Yeah, there's one.
So look, red letters, CSA.
Can I do this one? Have any, nobody was no text.
No, you're right.
This was 5.
Actually, there's 2 that were notated.
Yeah, this was 5 too.
Yeah.
This was 6. 7. And 8.
Right.
Okay.
Okay, we have a tie right now, and I didn't.
I missed the vote.
And you missed a vote.
I wanted to vote for number 2.
And the tie is 1 and 2.
Not anymore because he just voted for 2.
And I would vote for 2 as well.
And I'm abstaining.
1 for 1. Otherwise, second one was probably.
So the tie was between 1 and 2, you said?
Yeah.
1, and that's 2, and then we have plus 2 votes.
Right.
2. Okay. Democracy in action. 2 it is.
Okay. That was done by the way, a club member who's a,
Graphic art.
Yeah, he's a graphic designer.
Here's the thing. We got the number 2. Can everybody live with that? Yeah, that's a, okay.
Right.
Actually says what our investment is.
Yeah, well, actually, so let me, if you read the details on 2, it says contrast and basic design without getting bogged down with specific color choices. We can iterate with different color schemes to find one with color field is the base color of the T-shirt. So we can work with Steve more, perhaps refine it a little bit more as well.
Okay, so I want to move on to Dave Warner. You got everything. Brief outreach report.
Do outreach first?
Lights on.
Yeah, right now we're going to do outreach first. Lights on. That's fine. We've got Horizon. We've got a goes through, and we'll have a looks like 30% cloud cover on Friday night. That's Horizon Middle School. You can click on the calendar, see where that's at. We've had great people. I can use a couple of people out there for that event if you can make it out Friday night. And then just Prairie in November. There's Prairie Heights. She's out by PIR down south. So we're going to do an event down there, and then another Florissant also. That's for outreach that we have scheduled. Another Florissant in December as well. We probably won't see a lot more outreach scheduled in November and December. There's the Great Heights Star Party in Florissant. You can see where those are, obviously. In the past, from our last meeting, we had our Astronomy Day. Amount of support from the club. We had about 14. They gave a bunch of free NASCL stuff away to a bunch of the kids and people. We did solar astronomy. We had a great time. Garden of the Gods loved it. Astronomy Days again. In 2018 in collaboration relationship. About 700 you're doing, looking at the stars and looking at our mirrors on the sun. Then I speak. I mean, CSAS is simple. But the Saturday prior, we were out there all day from 10 until 4. We had made lots of ultraviolet great. Talked about the dangers of the sun, looked at the sun through our telescopes with great prominences. So we had about 6 of our outreach team members come out and help with that. So great support this year. Great. We had a great time. We had reached over 8,000 some people. We'll talk more about that at our Christmas party. So that's about all that I have for outreach. Once again, thank you for all your support and what we got going on. As far as what's up in the night sky, if you can here. Oh, we did Coronado High School Star Party too. That was the first time we were at a Coronado. We had about 40 people coming to look through our telescopes at that high school, so that was real successful. So what's up in November? I'm going to do this real fast so we can move on. Next slide. One of the things tonight is there's an asteroid into this month. There's an asteroid Iris constellation Aries. Have a graphic of that. I'll try to post this on our web. October 30th, the moon is 9 degrees backwards. Neptune is 29 degrees from the moon. Next slide. This will give the graphic. I have there's charts so you can where this asteroid Iris 7 is going to be constellation Iris, so you can see it. I use the comment last it's an asteroid. Next slide.
Should be a binocular object.
Yeah. So something to look colder, but still nice, clear skies this time of year to go look out. On November 5th, there's an Aldebaran moon at 8 p.m. our local time. So go check that out. That's going to be in the evening on November 5th. We have the North Taurid meteors of around 10 asteroids per hour, or meteors per hour. The Leonids are about 20 per hour. Those are more forming since the Leonid doesn't come up until late. And then on the 24th, Mercury's elongation east at 22 degrees from the sun. And a couple of November 22nd, at its greatest brightness. It's a dichotomy being where it's half shape, half full, half dark. November 26th, Neptune will be, again, 1.2 degrees north of the moon. So a couple of different opportunities to be able to find Neptune to the moon as your marker to find it if you haven't been able to see Neptune or Uranus in the next 6 months. Next slide. And then just kind of cover. You'll see that pathway of the moon is getting across that star. Really cool to go see a star being covered up by the moon. If you haven't seen that, there'll be opportunity for us in North America to see that. And then the Taurid meteor showers up there, and just ignore Jupiter in that, because that's not where Jupiter is. But I stole this. This was still a better graphic for me to use for showing that, up there above where from up in the east, and you'll have up by the 80s, that's where those Taurid meteor showers are going to be out there for several evenings looking for those meteors. And it's coming right out of the constellation Leo. And again, ignore the Jupiter. Next slide, please. And then the final thing that I have for our What's Up is you might notice the Big Dipper, or the Ursa Major, is down there parallel to the ground. And this is a where I reminded the Indians in southeast Canada this time for the bears go into hibernation, and it was those 3 stars on the back of the Dipper, the hunters that would climb onto the bear and they chop the head off, and that was what caused our leaves to turn yellow, orange, and red. Was the little Halloween for you there. So happy Halloween. That's all I have for What's Up tonight. Enjoy the nice guys. Same thing.
All right. Let's see. RMSS. Not
Right, we had a meeting over at my home actually on Sunday afternoon. This week I will get them for the rest of this year and next year leading up to the expo event. When we're looking also at the location, so in the next week, now all those dates should be up there. We have our theme and we have our design now chosen that's taken care of. We already have a number of vendors. More than I would tell you. Software Disk is now looking at coming over. You can do a presentation too when they're in here. That'd be kind of neat.
Peers are now reaching out to us. Yeah, that's great.
So I really don't have a whole lot more right now.
So one of the takeaways of the calendar events, the time we'll be posting the meetings, times, dates, locations for the RMSS. We do a combined and we do a combined RMSS planning followed by Starry Meadows, and so that's where I'll ask now. You're still here. Yeah. I was like, I ran out of the opioids for months. Just left it out. Time to say that one that says 22 on it. 1 p.m. RMSS Land Committee meeting. That was 2 days ago. That was 2 days ago. That's what they look like. Yes, that's what they look like. They'll be in the blue colored. So just look for that on the calendar when Tom gets that updated. So Al, I mentioned that we see these combined. RMSS, we also talked about Starry Meadows development. The recent discussing is power. Where we're at in terms of our portable power.
I agree. Basically, we've been looking at primary sources of power: generator, solar and generator.
The solar generator and solar with generator backup.
And that's about all I can say about it right now. We're in the discussion phase of that. We're kind of making a great attempt to get grid power. It's going to cost a lot of money. We got wind that the club that Ray Records in, what's the name of that? Nobody can remember.
Deep Space Exploration Society.
Pretty. When you do that talk, came in and talked about the vision. A guy fly out from Maryland back east. Like what they were doing, needed his $7,000 to bring electricity in. If anybody knows anybody like that, point them our way, please.
Yes.
That's all we've got.
Right.
The road's in kind of empty shape. Half of the road's been graded. It's so you can going up, and about halfway up you move over to the right-hand sidelines. Porta potty's in good shape.
And Tom and I were down there, Tom, 2 weekends ago, I think, and we installed the pier.
Right.
The metal pier on the concrete base of the observatory. There should be, but under the club news.
If you happen to wander down there and you see this funny look, that's the observatory to come.
Yeah. So that right there.
There we go.
Yeah. So now this is not super current. So what we've added right here is the pier for protruding out of this, of that hole. And so we've got that done, and the plan is now to get a posse together, probably during a work day next spring, to actually get the observatory building constructed, right? So all good, but I think, you know, that's kind of almost a finished project. It's the electricity we really want to get going on next.
It will appear to be a pier.
Okay, and let's see, I'm just kind of going through this kind of quickly here. How we said a little bit, Brian. So astrophotography special interest group.
Last month, we had an interesting discussion about what was a bit more of an advanced topic, deconvolution software, which is kind of really cool because it has the promise of being able to capture better photograph than your camera can take. Now, think about that. But that's the promise. The biggest note is that because next Tuesday is Halloween, and we normally always meet 1 week after this, it's been requested that we hold that back a week. So we won't be meeting this coming week, but 2 weeks from tonight. And if you are not on the list or contact, please give me your name and email, and I'll make sure that you get the information about that. It could change by that day, but right now I've been looking at, there's some interesting software out there that has an algorithm that allows you to take Milky Way photos better than you've ever done before, and that may be the topic for 2 weeks from now. Anyway, not at my house. If you don't know where that is, just give me your name and email, and I'll make sure you get the contact.
Okay, very good. And let's see. A couple of things that I want, just one thing I want to put out there. If you received the latest issue, the December issue of Sky and Telescope, looks like this. The lead article, Jupiter Rediscovered. If you may have noticed that the author of that is Dr. Fran Bagenal from UC Boulder, our friend, two-time speaker down at RMSS. So if you haven't checked it out, check it out. She's a really great writer. I mean, I love the way that she just explains things very clearly. So great to see Fran's got an article in the Sky and Telescope again. Observing reports. We have a little bit of time left. Vicki. Vicki is sitting over there with a box of books. So Vicki, tell us about your box of books.
We're clearing out the library for books we don't really need. Please come and grab some. They're great.
Free books, you know, after the meeting.
They're a little dated. You know, Latin.
So here comes the fun. Go ahead.
You already did it.
I said so are we. You missed it, right?
Okay, last thing we do, just a couple minutes remaining, observing reports. Now, nobody can claim that the weather has been crappy because there have been some really nice nights. I know it. You know it. So what have you guys been looking at? Floyd.
Planet 7.
Planet 7. Is that a new Netflix show?
You're in it, yeah.
Oh.
It's really easy to find. It's under Aries. If you go to Aries and look at the two stars, they point to a bright star that's in Pisces. And then drop down to the next star in Pisces. And right there, just to the right of it, is Uranus.
All right. Okay. Anyone else?
A couple of weeks ago, morning sky, you've seen Venus up there. I forget the exact date. It's about 2 weeks ago, where Mars was tucked up just a fraction of a degree up to the right of Venus. Picked them out naked eye in the morning sky. Really pretty.
Nice.
And then over the next several nights or mornings, you could watch Mars very quickly stretching away from Venus.
Okay. I remember being outside seeing Venus, but I never picked up on Mars being so close.
Yeah, it was. There was one morning where they were less than a half degree apart.
It was about 2 weeks ago.
That's right. Yeah.
Really?
It's in my WhatsApp.
Where was I? I don't know. Okay, anyone else? Observing reports? Okay, that I believe conducts this month's meeting. Does everybody have anything that,
Just make sure everybody had a chance to do the attendance sheet.
Attendance sheet.
And if we did have visitors, the cards are still there.
Visitor cards in the back. Okay, we'll see you next month, November, and coming up at the beginning of January, we will have Matt Russell sitting right here as our president-elect taking office. Jill Furman sitting back here will become our new treasurer. Fred continues on as secretary. Jim Urim is not here tonight. He continues on as vice president. And Dave Warner back here will be dual-hatted, not only as director of outreach, but also as the member at large. So does that give you 2 votes? No.
No.
All right, so I call this meeting adjourned.
Hey, Scott, do we need to put your?
Yes, and we need to